Hello and welcome. In this video, we're going to take a look at one very useful method for solving linear equations. If you have a system of two or more linear equations, then this is a way that we might be able to actually find a solution for all of the variables so that every one of the equations is satisfied. Now, you may be familiar with one method called the substitution method, and what that does is it relies on us taking any of the given equations, isolating a variable, and substituting it in all the other ones, and that does get rid of that variable, but it can be a very tedious process of having to repetitively do that until we get down to a single variable. Elimination, on the other hand, does maybe involve a little bit more manipulating with the equations right off the bat, but you can get down to a single variable in a very efficient manner, and it's a very consistent manner. So let's take a look. Here's an example. I've got 4x plus 3y equals 6 and 3x minus y equals 13. And I've given the basic principles of what we call the elimination here. So first of all, we have the multiplication principle. We can multiply both sides of any equation by a non-zero value. Now, what might not have been super obvious is using the idea of the addition principle, we can add anything to both sides of an equation. And as a result, that means that we can actually add multiple equations together, just term by term, and that will result in a new equation. Now, the goal of the elimination method is to try to create new equations that have fewer variables in them. And then, hopefully, once we get down to an equation with a single variable, it's easy to solve. So here, I've got two equations, and if I were to add these term by term, then you can see I would end up with 7x plus 2y equals 19. But my goal is to create equations with fewer variables, and I haven't done that. So just adding these two together is not entirely useful just yet. You have to use the multiplication principle first to creatively find some way to multiply both sides of any of these equations in order to result in addition that eliminates a variable. So you can see I've got term by term 4x and 3x. If I were to add them together, I will still have an x in my equation. But if I can find a way to multiply this whole term 4x by some non-zero value and multiply this 3x by some non-zero value, it's definitely conceivable that they could add up to 0. And same thing with the y's. I've got 3y and minus 1y if I want to put the 1 in there. And currently they don't add up and eliminate, but I might be able to find some way to multiply one of them by a non-zero value so that they do. And this is an easier case with the y's. I can see that I've already got one coefficient being positive and one coefficient being negative. So when they add together, they're getting smaller. I might be able to just take this bottom equation and multiply the entire thing by 3. Of course, with the multiplication principle, you have to do that same operation to both left and right hand sides. When I multiply by 3, I'm going to have 9x minus 3y equals 39. Now, I may not actually have to do anything to the first equation. I'm going to not multiply by anything. I'm just going to carry it over here and have 4x plus 3y equals 6. Now let's try doing the addition again. We've set this up in a way that the y's, term by term, add up and have 0 y's. Now, just making sure that I've multiplied the x by 3, I'm going to have 4x plus 9x now, and that will make 13x. And over on the right-hand side, I have 6 plus 39, which is going to equal 45. All right, well, unfortunately, this won't give me a very nice value of x. X is equal to 45 over 13. And there you go. Once you've got down to a single variable, then we can solve for x. Now, you still need to get a solution that involves all of the variables. We still need to figure out how to solve for y. And there's multiple ways to do this. Of course, you could go ahead and you could go back and rely on substitution and take this value for x and plug it into one of the two equations. Doing so will get rid of x and replace it with a value and allow you to solve for y. Now, your other option is to use elimination again, but see if you can eliminate the other variable. And it's good to see that as an example. We'll just write out the equations again and treat this much like we had before, but trying this time to see if we can eliminate the x. Now, unlike the y's, it was very easy to find a common multiple, where just I only had to multiply the bottom equation by 3. But in this case, I've got 4x and 3x. Now, the lowest that I might be able to find as a multiple of 3 and 4 would be 12 here. So I'm going to make sure that I take the top equation and multiply this by 3 this time, and take the bottom equation and multiply by 4. But hold up a second, I want these to add and cancel out. So one of these I'm going to multiply by a -4 so I can switch all of the signs while I'm at it. In doing so, I will end up with 12x, 9y, and 18, making sure that every term gets tripled. And on the bottom, switching the signs, -12x, +4y, and then when I take 13 times 4, now we'll end up with -52. All right, now let's try adding these together. And you can see that the 12x cancels with -12x. 9y plus 4y will get us 13y. And, of course, 18 minus 52. Once again, this isn't going to end up with a very nice value, but we can find that y is equal to -34 over 13. And there we go. We have a solution. We should probably state that in the terms of ordered pairs. You can imagine that this is really just a coordinate on two lines that intersect. And the coordinates would be 45 over 13, -34 over 13. And so that's the elimination method with two variables. It does get a little bit trickier, but you can still apply the same idea if you have 3 variables. Now, once we start getting into 3 or more variables, of course, the elimination method will take significantly more steps. You'll have to do a lot more combining equations in order to eliminate the x from all of the equations, not just one at a time, but try to eliminate it from all of them. And then maybe you'll end up with y's and z's, and now you can start eliminating y or z. Now, it's quite a long process. That's okay. We're going to actually find some way to sort of simplify this down into an algorithm, a routine that you can just do the same thing every single time and get all of your variables isolated. And that's really the job that we're going to be looking at here when we're taking a look at linear algebra with matrices. But that'll be coming up in a future video. Thanks for watching.